Hey guys, today we are going to be looking at higher order derivatives and differentiability. So higher order derivatives just mean that you're going to keep on taking the derivative over and over and over again. It's repeated differentiation. So the first derivative, what we've been finding the whole time during calculus so far, is just plain old f prime or dy dx. Now if we take the derivative of the first derivative, that's when we end up with the second derivative, or f double prime. Or d2y over dx2. Then f triple prime is our third derivative. F with the 4 primes gives me that fourth derivative. So as you notice, once we get past like the third derivative, you're counting those little tick marks, right? So it gets to be kind of a pain in the butt, and that's why when we watch that thing about Newton and Leibniz, why Newton's notation was not quite as helpful because it dealt with all those little tick marks. You gotta kind of count it out. So what we want to do is find the first, second, and third derivatives and then make sure we label appropriately. So to find that first derivative, remember our first derivative is going to be f prime of x equals. We'll bring that first power down, multiply, so we'll have 20x to the, subtract 1 from the power, so it's 3. Bring our power down and multiply, so negative 3 times 3 is negative 9x. Subtract 1 from the power, squared. Bring that power on down and multiply, so we'll have 14. Subtract 1 from the power, so that's just plain old x. The derivative of negative 9x is negative 9. And then the derivative of 2 is 0. So there's the first derivative. Now to find the second derivative, we're going to look at the first derivative and take the derivative of him. So we'll bring down that 3 and multiply, so we'll have 60x squared. Bring down my power and multiply, minus 18x plus 14. Then for that third derivative, we'll take the derivative of the second derivative. So once again, we'll bring our power on down, get 120x minus 18. So that's how first, second, and third derivatives work. You just keep on taking the derivative. I promise there's a reason we're going there with it. It's going to be next unit, though. Now we want to find the first, second, and third derivatives of sine squared x. So remember, if it's helpful, this is the same thing as sine of x squared. So we're going to have to use the chain rule since we have a function inside of a function. So we'll find our first derivative, dy dx. We'll take the derivative of the outside, so we'll bring down our power. Keep the inside. Subtract 1 from the power, so now the sine's to the first. And then we're going to multiply by the derivative of the inside. The derivative of sine is cosine. So there's my first derivative. Now we want our second derivative. So this is d2y over dx2 equals. So now when we take this derivative, I'm going to go ahead and we'll just keep the 2 with sine. So we're going to call 2 sine of x my first, and cosine of x my second. Since I have two things multiplying together here, I have to use the product rule. So remember, that's the derivative of the first times the second plus the derivative of the second times the first. So off to the side, if it's helpful to have the derivative of the first, the derivative of 2 sine of x is going to be 2 cosine of x. The derivative of the second, so the derivative of cosine, is going to be negative sine of x. So now let's find this derivative. Derivative of the first is 2 cosine x, times the second, which was cosine x, plus the derivative of the second, which was negative sine squared, or negative sine x, I'm sorry, times, and then times the first, so 2 sine of x. Now, since we're going to have to take the derivative of this again, I'm going to go ahead and clean this up. So this is 2 cosine squared x minus, because remember we have a negative sign times 2 sine of x, so we have minus 2 sine squared x. Cool, now let's find the third derivative. So d3 dy, or y over dx3 equals. Okay, so now once again, we have a chain rule going on because it's just like this situation up here at the top where sine squared x is the same thing as sine squared, okay? So we're going to think of this as 2 times cosine squared minus 2 times sine squared. That's how we're going to treat it. So we're going to bring down our power. We'll get 4. And then remember the inside stays the same, so we're still going to keep cosine. Subtract 1 from the power, now it's 1. Now we'll multiply by the derivative of the inside. The derivative of cosine is negative sine. Minus. Once again, we'll bring down that 2, so 2 times 2 is 4. The derivative, we're going to keep the inside the same with sine. Subtract 1 from the power is 1. And then we'll multiply by the derivative of sine, which is cosine. So we have negative 4 cosine x sine x minus 4 cosine x sine x. I wrote that in a different order so that way we could see these going together, which will give me negative 8 cosine x sine x for my third derivative. Differentiated. Now, you might think if you can find the derivative of something, you're able to differentiate it. Not necessarily. So a function is differentiable if it has a derivative at every point. So there might be a particular point inside of that function where my derivative doesn't actually exist. So for a function to be differentiable at x, the left-handed derivative and the right-handed derivatives have to be the same. So we're going to check limits. We're going to check those derivatives on both sides. So let's take a look at this first guy. So if we want to look and determine if the function is differentiable at x equals 0, if we go ahead and find the derivative of this part, so the derivative of 1 is 0, we'll bring down the 2 and multiply, so we have negative 2x. If we plug in what the slope is there, if we plug in 0, we'll get 0 over here on the left hand. Then down here we'll talk about the right-handed limit. So if we take the derivative of 3x plus 1, we just get 3. So my right-handed derivative and my left-handed derivative, one of them is 0, one of them is 3, so it is not differentiable at 0. Good deal. So here's how we'll know if a function is differentiable or not. There can be no corners or sharp cusps. So a corner would be like an absolute value function. You're going to see, because it comes to a sharp point there at the center. Other times you'll see cusps that look something like that. A lot of times those involve E, things. So if you get a sharp cusp, our function will not be differentiable there. You might have a vertical tangent line somewhere. A lot of times this happens when we're looking at root functions. Sometimes if we want to draw a tangent line in there, it would have to be a straight up vertical line. And so vertical lines, their slope is undefined. Also, if there's any discontinuity, your function will not be differentiable at that point. Now, things that are important to know. Differentiability implies continuity. What that means is if we know a function is differentiable at p, then we know that it has to be continuous at p. But flip it around, and that might not be true. A function might be continuous at p, but it might not be differentiable. For an example of this, let's think of, again, the absolute value function. That function is continuous from negative infinity to positive infinity, but it has a sharp cusp there, so it's not going to be differentiable. So for all real numbers, x squared minus 6x, is that differentiable and continuous? Differentiable but not continuous. Continuous but not differentiable, and neither continuous nor differentiable. Now, first of all, we can find a derivative of this. The derivative is going to be 2x minus 6. X squared minus 6x is, that's continuous. Its derivative is continuous. So this guy is going to be differentiable and continuous. You can also take a look at the graph, and you'll see that this guy is just a parabola. Okay, let's look at this next one. For all real numbers, f of x equals the absolute value of x minus 2 is differentiable and continuous, differentiable but not continuous, continuous but not differentiable, or neither continuous nor differentiable. So, if we think of this guy, this is what an absolute value function looks like. It got moved over 2 to the right, so this is at 2, 0. Now, an absolute value function is continuous all the time, right? But remember, because of a sharp cusp or a corner like that, it means it's not going to be differentiable. So in this case, it's continuous, but not differentiable. Now on this one, let me go ahead and redraw this notation for a second. This is our ceiling function. So for all real numbers, x minus the ceiling of x is all the options that we looked at before. Now, right now, you're probably like, first of all, I don't remember ever seeing ceiling inside of my formula book, so I have a feeling that that guy is not going to be differentiable because I don't have a derivative of it. You'd be right. But also, it might be helpful to look at a graph. So when we graph 1 minus the ceiling of x, we can see here we just keep getting a bunch of little line segments. So we can see that that is not continuous at all. So since we're not continuous along that function, that means we're also not going to be differentiable. So it is neither continuous nor differentiable. So on this next one, we want to know for what domain is 1 over x differentiable. Well, let's think about this one. We have to know where is it continuous. Or another thing is, let's find out where it's not continuous. Let's find out where it's not differentiable. It's not going to be differentiable where it's not continuous. Remember, a rational function like 1 over x is not going to be continuous wherever our denominator is equal to 0. So we'll take our denominator and set it equal to 0. So that means we cannot have a value at x equals 0. Now if we took the derivative of this, remember he is x to the negative first. So if I were to take the derivative of him, we would be looking at negative 1 over x squared. Now once again, on that function, where is that derivative not continuous? At x equals 0, right? When we take x squared and set that equal to 0. So my function is differentiable everywhere except for 0. So from negative infinity until 0, we'll use parentheses to skip over him, and then from 0 to infinity. So for this next one, we have to figure out where is our function continuous. So we know that this function looks something like this. It was usually at 0, 0, but we got shifted 3 over to the right. So now we're at 3, 0 for that beginning point. So we don't actually have any values less than 3, right? So we can't differentiate on with that part. So we're going to be able to differentiate from 3 on. So from 3 to infinity. All right, good deal. See you guys later.